Hey everybody, it's Mr. Hicks coming to you for our last physics video of the year. It'll be okay. You guys will be ready to go. You're graduating soon. You're moving on. That's good stuff. So I have my sunglasses on for a reason, not just because I want you to think I'm cool, because we all know I'm really not. The sunglasses are for later. If you guys have a pair of sunglasses, you're going to need them for experimentation later today, whenever you're watching this or when you're driving your car and you're at a stoplight. Specifically, if you have polarized sunglasses, that's going to be the key. I don't have polarized sunglasses. My one pair of polarized sunglasses that I did have were really old, and I've lost a few pairs since then, and broken a few pairs since then. These are just regular cheap, like $5 sunglasses. They are not polarized, and when it comes right down to it, what I salvaged from the room before the tornado, I didn't grab my polarized filters. And I do have them salvaged, but they're not salvaged at my house. And it's 9 o'clock at night, and I'm not driving somewhere to get polarized filters for this lesson. Sorry, call me lazy, but we're going to finish up talking about light and some important concepts. So I'm going to narrate again. I'm going to screen share to the little document that I've been trying to use as our outline, our guide. Last lesson today was this morning, and we talked about the white light and colors. We talked about the electromagnetic spectrum, and we talked about transparency, where light can go through something. We talked about the fact that light can make its way through glass because the material that the glass is made of has a frequency, a resonance type frequency that's compatible with light. But other parts of the spectrum are not compatible with it. For example, I mentioned the fact that UV light is not compatible with glass. UV doesn't make its way through glass. That's a good thing. But now we need to talk about the concept of translucence. Translucence is similar to transparency. Translucent means that light can actually pass through it, but it doesn't pass through clearly. So essentially, it's something like frosted glass. If any of you have a shower with a shower door, that typically is going to be translucent glass. The shower door, you could see the silhouette and the basic, body of a person behind the shower glass door, but you can't see all the details. That's the way it's supposed to be. If you go somewhere and they have a shower door and it's completely clear glass, there's no privacy. If somebody else walks in on you, that's not good. You might think, well, who walks in on someone in the shower? Family does. All right, family walks in on people while they're in the shower, especially if you only have one bathroom in your house. I don't know if any of you have ever lived under those conditions, but I grew up in a house where there's only one bathroom and you got walked in on by everybody. So translucence, light passes through, but not clearly. You might even consider something like colored filters, where light gets through, but everything is colored a certain color, and nothing is clear. I don't know if you've ever looked through colored filters, but colored filters if it's a green filter, it lets green light through, but nothing is clear. There's distortion to the image. It's not like going through clear glass. So translucent lets light pass through, but there's no real clarity to the image. So frosted glass, light diffusers on lights. I don't know if you guys can, in your mind, think back to the classrooms in the school. They have fluorescent lights. Well, there's 4 light bulbs in each of those lights, and there's a translucent piece of plastic that's in between the light bulb and us. It lets light through, but it doesn't let you see the detail of the light bulb. It diffuses it. That would be translucent. Okay, so let's talk about the concept of opaqueness. Right? And after we talk about the concept of opaqueness, we're going to talk about polarization. So if something is opaque, essentially what that means is it does not let light through, right? So it's pretty simple. A wall is opaque to light, right? You can shine a flashlight at a wall, and guess what? The light doesn't go through the wall. It gets blocked by the wall, right? That's opaque. Like my hand is opaque to light. I cannot see the light that's coming at my hand there. It didn't get to my eyes. It blocks the light. I think you guys get that. Opaque means it blocks the light. So light essentially doesn't get through it, but really light can do a few different things here with an opaque object. One thing that the light can do is the light can actually reflect off of the opaque object. Now, it kind of depends on the object that's opaque. Not every object that's opaque to light is going to reflect light. Think about a drywall wall. Right? A drywall wall or a wooden wall, like they don't really reflect light. Light hits them, but light doesn't really, bounce off them like light bounces off of a mirror or light bounces off of a pair of sunglasses. Can you guys see light bouncing off my sunglasses? Right? You can see all sorts of, images on people's sunglasses when they wear them. It depends on the nature of the material. So typically, something that reflects light is something that's very metallic, very smooth, very polished. Okay, for some reason, I have a fork in here. A fork is metallic and polished, and it reflects light. Right? You can see. Right? It's not really weird. I used a fork to eat a meatball this afternoon, and I just licked the fork and put it down over here. So that's why I have a fork in here. But the metal reflects the light. It's shiny. The nature of the material is such that light hits it and it energizes the electrons of the light, and then those electrons bounce the light back off. That's the concept of reflection. Wood doesn't typically do that. Many types of glass actually reflect light. A mirror is actually a piece of glass with a metallic film behind it. And that metallic film behind it is doing the reflecting. The light goes through the glass, it hits the metallic film, bounces off. Technically, water can kind of be opaque. I don't know if you've ever been out on a boat on water and you look down and you really can't see into the water because the light is hitting it and bouncing off and reflecting. So in some senses, depending on the angle, light is opaque to that. Light reflects off of it. Right now, something that's opaque with light is also going to cast shadows, right? Because the light can't get through it. So essentially what it's doing is it's blocking the light. So, right, there's a shadow on my face, right? Because the light is not getting, well, at least full direct light is not getting to my face. I can put my hand here in front of my light, which is right here, and you can tell, right? You can tell that there's a light there because my hand is blocking the light. And so it casts a shadow on my face. Now, depending on where the light source is and how close the blocking object is depends on the type of shadow, right? If I'm going to pick up this video here to be my blocking device instead of my hand. If the blocking device is close to the person, right, you can see one type of shadow. If it's really far away from the person, closer to the light source, it does different kinds of shadows. So you can see when this blocking source is close to my face, there's lots of light hitting over here behind me. But when this blocking device is really close to the light source, right, there's a lot of light. This might work even better if I stop the share. There we go, right? If I put it real close to my face, it puts a shadow on my face, right? But it's a small shadow because my blocking device is really far from the light source. If I move it really close to the light source, did you see how the shadow is much different? It actually blocks like a lot of light from getting to that whole window behind me, right? So it depends on where your object is and where your light source is. Right? So, you know, there's all sorts of unique things that can happen with shadows. Now, typically in the world of physics and the world of astronomy, when we're talking about shadows, we're not really talking too much about, you know, a shadow that's cast, you know, from a light source, you know, in a room. We're really talking like larger scale astronomy, you know, solar eclipses versus lunar eclipses. But you could be discussing shadows in the world of physics. It may, you know, on a smaller scale, like a room scale, if you were designing a room, designing rooms for like photography and that type of stuff. That's where you'd want to know where light sources are and how far away they are and what objects, you know, and how the light is going to reflect when the flash happens, right? That's kind of, well, that's very much physics, but there's not a lot of physicists out there who do that that type of stuff. It's not something that's a real huge area. But in astronomy, you got solar eclipses and lunar eclipses, which is where there's shadows. And you got some shadows which are real big, some shadows that are real distinct, some shadows that are small. And there's actually some places where you have really dark shadows and light shadows in the same general location. One of them is called an umbra, and one of them is called the penumbra, a full shadow and a partial shadow. You can look that type of stuff up. So you've got these different kinds of shadows that are made from opaque objects. And then with opaque objects, narration time again, back to our screen share, right? You've also got the fact that opaque objects can actually absorb light. I know that we said that some of that can happen with transparent objects as well, but opaque objects where the light's not getting through it, if they're getting hit by light and it's hitting them and bombarding it and hitting it and hitting it and hitting it, many times it's actually getting absorbed. And as it's getting absorbed, it gets hotter. Right? So those are some of the things that happen with opaque objects when they're opaque to light. Light gets reflected, it casts a shadow, and then also light can be absorbed. Now, we did talk about the fact that light is a piece of the electromagnetic spectrum. Light is just a small part of the electromagnetic spectrum. And we could actually talk about the concept of opaqueness with other pieces of the electromagnetic spectrum. So let's do that for a few minutes. Let's talk about something that is opaque to radio waves. We kind of alluded to this when we were talking about transparency. We said that the walls of your house are transparent to radio waves. Radio waves go right through the walls of your house. They get picked up by a radio transmitter. Microwaves are transparent to the walls of your house. How do I know? Because we have these things called cell phones. I don't know where mine is. Doesn't matter. Don't need it right now. It's 9:30 at night. Your cell phones operate off of microwaves and interacting with satellites. Right? So the microwaves go right through your house. Doesn't matter. But we know that radio waves and microwaves cannot go through granite mountains. When you drive through the tunnel, one of the 2 or 3 tunnels that I know of here in Chattanooga, you drive through, guess what? Your cell phone doesn't work too well going through the mountain, and neither does your radio wave. It doesn't work going through the mountain. Just the wave can't get through there. Those waves are opaque to granite, to rock, especially thick layers of rock. You could even say the same thing. You know, ultraviolet light is opaque to rocks. UV does not go through rocks. You don't have to worry about, if you're in a cave, ultraviolet light from the sun making its way through the dirt and the rock of the cave and giving you sunburn. Doesn't happen, right? Now we can talk about, you know, the fact that your skin and your flesh are transparent to X-ray, but your bone is not transparent to X-ray. Your bone is opaque to X-ray. your bone actually blocks x-rays from getting to the film that's underneath it. So like they used to put a piece of actual film underneath there. Now they don't really need to put film there. They can just put like a device that reads the x-rays, and it's electronic, and everything just goes electronically. They don't even have to do film x-rays anymore. My guess is that most of you, if you've had an x-ray taken, you're from the generation where it was all digital. Me, they actually had to put film underneath my bones when they would x-ray them when I was younger. Right? So the x-ray it's transparent to the flesh, but it's opaque to the bones. So we can sit here and go all day long. This type of piece of the electromagnetic spectrum is transparent to this, but opaque to this, transparent to this, opaque to this. We could go, all day long on that, but we won't. So, one last thing that we'll do, gamma radiation. Gamma rays are transparent to skin, flesh, bone. We talked about this gamma knife surgery. Right? Gamma rays can go through us, and they can actually do damage when they do that. They don't do enough damage to turn you into the Hulk. I know you're thinking the Hulk. All right, that's not real. Too much gamma radiation will kill you. Right? Doesn't turn you into the Hulk. It kills you. But gamma radiation is going to be blocked by certain things. If you want to block radiation, you need to have really thick concrete lead walls, right? So radiation from like nuclear reactors, that radiation can be blocked by building heavy, dense, thick metal and concrete walls. Just got to build them thick enough, the radiation can't get through. It's opaque to that. Right. So we're spending more of our time talking about light, but we can talk about the other pieces of the electromagnetic spectrum as well. Now, this is a topic that I really, really like. I love the topic of polarization. Polarization is awesome. Okay. This is super, super practical. This is where sunglasses come in. If you've got sunglasses, or you and your mom, or you and your dad have sunglasses, or you and a sibling have sunglasses, you guys have to get your sunglasses out. You got to test this. You got to pay attention to this polarization thing, because this is super awesome. This is super, super important. So we're talking about polarization. And I realize we're not looking at the shared document. We're just looking at my weird face with sunglasses on. So I'm going to go to the shared document so we can see polarization. Right? So before we go too deep into polarization, what we've got to understand is that let's talk about light coming from the sun. But technically, this could be light coming from almost any light source. Right? The light that's coming from the sun has light waves that could be traveling in a wave in an up and down manner. But what's to say that the sun is not putting out waves that are vibrating left to right? What's to say that the sun is not putting out waves that are vibrating on this angle, on this angle? When it comes down to it, light that comes from the sun is being emitted, and it's vibrating on many different planes: a vertical plane, a horizontal plane, an angled plane, a shallow angle, a steep angle. The light that comes from the sun is just emitted in all these different planes. Okay, so the light comes from the sun and it damages our eyes, it makes us squint, so we put on sunglasses, right? That's a natural thing. But you see, there's a situation where light can be even more intense than just what normally comes from the sun. I'm sure every single one of you that has driven has, on a sunny day, pulled up behind a car, and you have seen a glare come off of the back window of the car. Or if you've been on a boat and you've been standing on the boat looking out, you have seen glare reflect off of the water while you're on the lake, right? What that is it's normal sunlight bouncing and polarizing and coming and hitting your eyes, and it's more intense. Polarized light is light from a light source that has actually hit something, reflected, and it has aligned, and it's kind of come in phase with other light waves. right? So think of it this way. The light coming from the sun, and it's hitting, I learned this on a boat with my father-in-law. So I'm going to use the boat illustration. Light coming from the sun has waves that are vibrating horizontally, vertically, on an angle. Those light waves are coming towards my face, sunburning me while I'm on the boat. They're coming to my eyes so I can see the sun. But the sunlight is hitting the surface of the water, and then it is actually bouncing off the surface of the water. And as it bounces off the surface of the water, the ones that are coming like this and they bounce off the surface of the water, they bounce and they turn. And the ones that are coming like this hit the surface of the water. And what happens is many of these light waves hit, and then they actually kind of line up together. And as they line up together, they become in phase. Like they're kind of become like in union with each other. They become more intense, right? Because now it's not random light waves traveling in different planes. It's light waves that have aligned and becomes more intense, and you get that glare off the water. That's what's called polarized light. It's kind of focused and aligned and more intense. Polarized light is focused and aligned and more intense light. And that glare is way worse on your eyes. If you're just out and about and it's a sunny day, that's not that big a deal. But if you're at the water, or if you're in a car behind another car and there's glare coming off, that glare really hurts your eyes. You got to squint a lot. All right. Well, that polarized light is more intense, and that's where sunglasses come in. Right. Regular sunglasses, they're just blocking some sunlight from getting in. But there are sunglasses that are polarized sunglasses. What they have is, on or in the nature of the material of the sunglasses, there is a polarized filter. Right? There's a polarized filter. And what you have to do is you kind of have to think of it as a filter that lets some sunlight through but blocks others. Right? So essentially, a polarized filter will block 50% of the light, approximately 50% of the light that comes through. Because think of it like a filter. Like there's light waves that are vibrating in a pattern, up and down, up and down. And there's a filter that's kind of oriented in this fashion. Well, how is a wave that's vibrating up and down going to get through a filter like this? It's not going to get through a filter like that, at least not very easily. So any of the up and down waves, right, are going to get blocked by a filter like this. But any of the horizontal waves can actually make their way through a filter like that, because it's vibrating in the same direction as the filter is oriented. So that's where polarized sunglasses come in. If you have polarized sunglasses on, right, the orientation of the filter on your glasses blocks a certain type of wave vibration, sunlight vibration. And so it essentially knocks off that glare. I remember the first time I learned this, I was out fishing with my father-in-law, and I thought the guy was nuts. You know, that's not unusual for son-in-laws to think their father-in-laws are nuts. My father-in-law is a great guy. I just had no experience fishing, and I really had no experience with sunglasses. I never really wore sunglasses. We were out fishing together, and he's like, "Whoa, did you see that fish up near the boat?" I didn't see some stupid fish up near the boat. He was always talking about, "Oh, did you see that fish following my lure? It almost took it." He's always making up, I thought he was making up fish stories. I'm like, this guy's a normal fisherman. He's just making up stories. I'm like, I don't see anything that you're seeing. He's like, all I see is glare. He's like, oh, you need to get a better pair of sunglasses. So he gave me a polarized pair of sunglasses, and it was amazing, right? The polarized sunglasses took all the glare that was polarized light glare bouncing off the water and like eliminated it. And it actually made it so much clearer to see down in the water. I realized my father-in-law is not nuts. My father-in-law is not lying to me. He's got good sunglasses, and he actually was seeing fish following lures. It was amazing. Like when you're on the water and you don't have sunglasses, you might be able to see a foot into the water, or 2 feet into the water, but then it gets kind of dark and murky because light is bouncing, light is being absorbed by the water. But when you take the glare away, you can see deeper in the water because the glare is not blocking, like you are seeing deeper in the water. He was actually seeing fish. And now if I go fishing with him and I have a pair of polarized sunglasses, I can see a whole lot more in the water because it's blocking the glare and it's letting me get a clearer picture down into the water. And that's why you want polarized sunglasses when you're driving a car too. If it's a really sunny day and there's glare coming off of people's windows, the polarized sunglasses will block that glare. And as that glare is blocked, that actually makes it easier on your eyes and gives you better vision for driving, right? It's really a beneficial thing. It essentially blocks out 50% of the light and does a great job of blocking out glare. It's really good for eyes. So that's where I learned it, fishing with my father-in-law. He's a really smart guy. He taught me a lot about polarized light and that really practical thing. Now, here's where the sunglasses come in. If you have polarized sunglasses, right, what you need to do is get 2 pairs of them. And you got 1 pair of sunglasses oriented this way, and then you take another pair of sunglasses that are polarized and oriented this way. And what happens is, it's like taking 2 filters, and one filter is oriented this way, which blocks 50% of the light, and another filter is oriented this way, which blocks 50% of the light. And what happens is, like if you orient them at 90 degrees to each other, one horizontal filter, one vertical filter, 50% is blocked, another 50% is blocked, it essentially blocks 100% of the light. And this is where I have failed you as your teacher. I should have remembered when I was salvaging science equipment last week. I should have remembered to get the stupid polarized light filters, because I could hold a polarized light filter in front of this camera and it would block 50% of what's going into that camera. And then I could take another polarized filter and turn it to 90 degrees and there would be 0 light going through to that camera. You would see nothing. And it's so cool. You can actually have, right, see there, you can still see me through those glasses. I could put a second filter just oriented like this and I would be completely gone. You would not see me at all. You can still see me. There's my nose, there's my mouth, there's my eyes. Like you can still see me in there. If you had 2 polarized light filters oriented at 90 degrees to each other, all of the light is gone. It's amazing. It's awesome. So get yourself some polarized sunglasses. You and a friend, when social distancing is no longer there, you or mom or you or dad or you and a sibling, if you've got polarized sunglasses, take one, orient them like this, and take the other and put the lenses over each other. 100% of the light will be blocked. It's awesome. It's an amazing thing, and it's really protective for eyes. It's really good for eyes. And let me tell you this, if you don't wear sunglasses and you don't wear hats to shade your eyes and you don't take care of your eyes, it can be very, very damaging. I have a buddy, he's been working outside for years and years and years and years. He operates heavy machinery. His dad has been doing it for, well, his dad's 80 something. His dad's been operating heavy equipment for over 60 years. And his dad never wore sunglasses. And his dad's eyes have been severely damaged by the sun and all the work that he did outside. And what ended up happening was he almost went blind in one eye and then almost went blind in another. He had to have like reconstructive surgery for like the retina of his eye because it was damaged by so much sunlight and not wearing sunglasses, right? So you gotta take care of your eyes if you're outside a lot. My buddy, his dad's eyes, very damaged. He has really good sunglasses, wears them when it's really sunny, takes care of his eyes because he doesn't want to lose his eyesight, you know, and it's key. It's really important. So we take care of our eyes. And, you know, that's just kind of a greater application. We take care of the body that God has given us. We don't abuse it. We don't waste it. We take care of it because, you know, God gave it to us to steward it, to use it, to honor and glorify him. And because if we're his child, his Holy Spirit's living inside of us. So it's always best to take care of it the best that we can. All right. Well, it's getting kind of late. We've been going for a few minutes and this is our last physics lesson. We will try to connect on Friday. You guys said you don't want to connect at 8 o'clock in the morning. I don't know why. We'll set up a time to talk, you know, late morning and just, you know, get together for one more time to have a good time and finish off our class. So I hope you guys are having a good day. Happy Thursday. Happy last real day of classes. I look forward to seeing you when we have more opportunity due to the lifting of the quarantine, and really look forward to graduation night with you guys. Have a good one. This is Fizz Hicks signing off.